All right, today we'll be presenting the wind project. I'm Cesar Cantu.
I am Joe Cardenas.
I'm Connor Ewing.
I'm Rania Sapa.
And I'm Zachary C.
We're group 2. This is our outline. We'll be discussing the title slide, outline, introduction / motivation and objectives, background, methodology, results and discussion, conclusion, references, and dependencies. A little introduction.
So the conversion of wind to usable electrical energy has accounted for 22% of new capacity for the United States in 2022. And with that, electrical vehicle sales have increased over 55% in 2022. The whole purpose of this project is to design a hydrogen fuel station for some vehicles powered by wind energy turbines. The motivation for this project is to meet the market demand for zero emissions power generations and vehicles. The wind energy currently provides 28.6 of energy generation in Texas and is second only to natural gas. Currently, California is the only state with hydrogen-powered vehicles. The objective of this particular project is to determine the amount of hydrogen in kilograms needed to refuel 10 Toyota Mirai, as well as determining the size of the electrolyzer and battery system needed to hold the charge, and also to develop and design a wind energy generation system to supply power to the electrolyzer.
So a little bit of background on the chosen hydrogen fueled vehicle, the Toyota Mirai. For the 2023 model, it can hold 5.6 kilograms of hydrogen capacity, and that's between 3 tanks. It has a 402-mile range, and it can refuel in about 5 minutes, which is a little bit faster than other electric cars. And it also produces zero emissions, just water. So a little bit of background we also had to look at to design the wind system is we had to look at the Houston wind speeds. So we found 2 different sources. The first one we found collect data back from 2010 till now to 2023. And the average wind speed in Houston was about 4.11 meters per second. We found a more current data range that actually altered. And with that, we found an average wind speed of 5.03. So here's a little bit of our layout. So first, you're going to have the wind that is going to turn the blade turbines. From there, that's going to send mechanical energy to both the yaw motor and the gearbox. So the yaw motor is going to turn the turbine into the face of the wind, and the gearbox is going to send mechanical energy to the generator. From the generator, that's going to produce a direct current that's going to be sent to our battery, which will store the energy. And from there, the inverter is going to pull the energy from the battery, also in the form of direct current. From there, the inverter is going to change the direct current into alternating current, which will be sent to the electrolyzer. Also sent to the electrolyzer is going to be distilled water or pure H2O without any salt or minerals in it. And from there, from the electrolyzer, we can send hydrogen separated from the oxygen into our storage tank. And from there, we can send that to our 10 Toyota Mirais. So some assumptions we have to have with this layout is that we're going to have no electrical losses from the generator to the electrolyzer. For example, so no losses from resistance of the wires or anything like that. We're also going to have no system degradation from wear and tear. So we're going to assume that this is a perfectly new system. And we're going to have no connection to the grid. It's going to be standalone. And we're going to assume that we have an air density of 1.225 kilograms per meter cube.
For our key equations, we have our wind turbine efficiency and we have our instantaneous power of wind turbine. Next. And working backwards, so for our hydrogen needed, we have 5.6 kilowatts. For So for 10 Toyota Mirai, it takes 56 grams of hydrogen. And for our electrolyzer efficiency, it equals 0.95. And to produce 56 kilowatt of hydrogen, we need 7.81 to times 10 to the 6 kg. And so here's our area equation that we used. And within 24-hour period, we need 87,743 watts needed. For our minimum swapped area needed, it's 7,312. Minimum diameter needed is 96.5 meters. And more information regarding these numbers and how we calculate it is available in the Appendix E. For our methodology, for our wind turbine diameter, we used 109. For our area, it's 9,332. For our CB, 0.42, NG is 0.75, and B is 0, NM we got 0.95, and 56,000 grams of hydrogen was needed to fill 10 2023 Toyota Mirai.
A little details of the Goldwind GW 109/2500. This actually has no gearbox, which reduces the potential issues common in conventional designs. Features a permanent magnetic generator, or PMG, for efficient operations with minimal losses. The PMG has only one moving part, the generator rotor, in contrast to over 13 gears and hundreds of other parts in traditional gearboxes. This also eliminates the need for electrical feed excitation, minimizing energy losses. This is also equipped with a full power converter for reactive power feed, compliance and grid code requirements, and low voltage and zero voltage ride-through capabilities. A little bit about our methodology. The average wind speed of 4.11 meters per second. The Goldwind GW 109/2500 produces approximately 100 kilowatts. The direct land use for wind turbines in the U.S. is 3/4 of an acre per megawatt of rated capacity. A 2.5 megawatt wind turbine, for example, in our case, would take about 2 acres of land.
Okay, so as again stated previously, our specification is the Goldwind. The turbine itself starts at around 3 meters per second, and the cutoff is 25 meters per second. The diameter is 109 meters, and the swept area is 9,332 meters per meters squared. Here is a graph showing the power output versus wind speed. Here is a chart using values from the Global Wind Atlas and Willy Weather over a 1-hour period. From these values, we managed to produce 120 kilograms of hydrogen with an average of about 5.03 meters per second for velocity. At a lower wind speed of 4.11 meters per second average, we also managed to produce enough to meet our hydrogen needed, which was 56 kilograms.
And in conclusion, to conclude all our finding, so the amount of hydrogen needed for 10 Toyota Mirai is 56,000 grams. And then for our turbine that we chose meets the specification power needed to refuel 10 Toyota Mirai. And also for our electrolyzer, it includes a production capability of 2,160. And for our overall total system efficiency is 0.284. So this is all our references that we used for our project. And thank you for listening.
Thank you for joining us.